In this video, I'm going to show you how to solve this particular circle geometry problem. So the problem states that the triangle TXY has its vertices lying on a circle. The tangent at T intersects the secant XY produced at Z. The point R lies on XY, and RT intersects the angle XTY. So prove that TZ is equal to RZ. So let's prove that. If we were to prove that these two sides are the same, so let's look at triangle TZR. So if these two sides are the same, if TZ is the same as RZ, then triangle TRZ is an isosceles. That's probably the direction we want to take in solving this circle geometry question. So let's look at properties of isosceles triangle. So one of the main properties of isosceles triangles are base sides are equal. And that's actually what we want to prove. We actually want to prove that TZ is equal to RZ and base angles are equal. We should show that RTZ is equal to angle ZTR. We'll use the second property as our strategy for solving the circle geometry problems. So I'm going to scroll down because we actually haven't started proving the question yet, but I'm going to scroll down so I have the diagram again without all the scribbles I've actually done on them. So scroll down to a brand new diagram and we'll start doing our proofs. Keep in mind what we want to prove is we want to prove that these two angles here are equal. So if we can prove that these two angles are equal, then we can prove that the two base sides are also equal. That's what we want. So we'll start with a fresh diagram. Let's start with marking our angles with letters so it makes it easier for us to solve later on. So let's let angle XTR equal to alpha. So if we know that this angle is equal to alpha, then angle RTY is also equal to alpha because it's given. So the diagram's told us that RT intersects angle XTY, so therefore these two, the two angles that the intersecting line has cut, are equal. So we know that these two are equal. So now what we're going to do is I'm going to focus on the tangent. So I'll write my notes down here. Let's focus on the tangent TZ. So before we begin with the tangent TZ, so let's look at the properties of tangents. So tangent properties. So tangent properties are, one main one is tangents are perpendicular to radius from center. So that is, if you have a radius drawn from the center, it meets the tangent at right angles. So another property of tangents are two tangents are equal distance from an external point. Distance from an external point. So that is, if I have two tangents to a circle and they meet at an external point, these two tangents are equal. This property is also not very useful to us because we don't have two tangents, we only have one tangent. This line here isn't a tangent. So I'm going to rub that out. That line here isn't a tangent. So let's look at the third property. So a third property of tangents is that the angle made with the tangent and the chord is equal to the angle in the alternate segment. So angle made with tangent and chord is equal to angle in the alternate segment. That is very abstract, so if I draw a diagram, you know exactly what I mean. So scrolling down a bit, so drawing the diagram looks like this. So angle made with the tangent and chord, this one here, is equal to the angle in the alternate segment, which is here. So that's our sailboat rule. This is actually the rule that I want to use to prove this circle geometry problem. Okay, so that's a lot of writing. We'll scroll down and I'll have a new diagram for you actually. Scroll down. Scrolling down some more. I'll get a new diagram up for you. There we go. Brand new diagram, move it over. Okay, so back to the question. So the original question was, we've proven that these two angles are already equal. So these two are already equal to alpha. Now we're going to focus on the tangent. So TZ's our tangent, and I'm going to highlight the triangle inscribed in the circle so that we can use our sailboat rule. So that's the diagram with all the information that I want highlighted. So focusing on our tangents TZ and the triangle inscribed in the circle, one of the properties of tangents is that the angle made with the tangent and the chord, so this angle here, is equal to the tangent in the alternate segment. So this angle here, we'll let angle ZTY equal to beta. We call it beta. We know that angle ZTY equals to angle TXY, and the reason is the angle made with tangent and chord is equal to angle in alternate segment. So that it's a mouthful, but that's the proof. So this one's also equal to beta, so therefore angle TXY is also equal to beta. So now what I want you to do is I'm actually going to want you to focus on another triangle. So let's look at triangle TXR. So if you're looking at angle TXR, which is this one here highlighted, so we have an exterior angle TR, we'll call it TRZ. We can see that the exterior angle TRZ is equal to the addition of the two interior angles. So that means it's equal to alpha plus beta. Now let's look back at our original isosceles triangle. So let's look back at in triangle TZR. You can see that angle RTZ is also equal to alpha plus beta. So in the diagram here, alpha plus beta. Sorry, I didn't give the reason for this one. This is exterior angle. We can also see that RTZ is equal to alpha plus beta. Therefore, since both of these angles are equal to alpha plus beta, we can say that therefore TRZ is equal to angle RTZ. And since we've proven that these two angles are equal, then we can say therefore triangle TRZ is an isosceles triangle. Isosceles. And the reason being base angles are equal. So if TRZ is an isosceles triangle, then TZ must equal to RZ. So to conclude, I'm actually going to write the proof out again, or with the summary of the proof without all the extra theory. Yep, scrolling all the way down. So here's the proof without all the extra bits. So we'll start off with let angle XTR equal to alpha, therefore angle XTR is equal to angle RTY, and they're both equal to alpha, and it's given. The next step was we were looking at tangent properties. So we stated that we let angle ZTY equal to beta, and we've shown that angle XTY is equal to angle TXR, and they're both equal to beta. And the reason behind that was angles made with tangent and chord angles made tangent and chord is equal to angles in alternate segment. Then we moved on to looking at the other triangles, I think. So in triangle XRT, we know that the exterior angle TRY is equal to alpha plus beta, and that reasoning is exterior angle in a triangle. And now we referred back to the original isosceles triangle. So in triangle TZR, we've shown that angle RTZ is equal to alpha plus beta. And we also shown from above that TRY is also equal to alpha plus beta. Therefore, we can say that triangle TZR is an isosceles. An isosceles triangle, and the reasoning is base angles are equal. Therefore, the last proof is TZ is equal to RZ. And that's how you do that question.